Good evening, everyone. I'm Rui Costa. I'm the director and CEO of the Zuckerman Institute that many of you know. So the Zuckerman Institute is an attempt of Columbia to bring many of the folks that are interested in researching how the brain works together into a center where they can interact and hopefully go further. We have engineers mixed with psychologists, with neuroscientists, with theorists, with psychiatrists, with neurologists. And so it's an experiment in Manhattanville campus. We have the Stavros Niarchos Foundation as a partner in this experiment, and with their support, we've established this Brain Insight lecture series. And tonight, we will have a talk by Daniel Wolpert. That's What's a Brain For? A Moving Story. And this type of lectures is very important to us for several reasons. First, we have our scientists talk to the general community about their science, hopefully in a way that is understandable, but also in a way that is not too superficial, so where you can get something new to take home. In addition, we have a Brain Insight Teacher Scholars program where some of the teachers and the students are here, and some of the materials of the lecture are then transformed into real curricular materials for lectures throughout the schools, and these are then taught at many schools, and they are available open source in our website. And third is in the format that we've adopted now, as you'll see, we have a more established scientist, in this case Daniel Wolpert, give the lecture, but then a young scientist comes and introduces the lecturer, and then they engage in a scientific discussion with Q&As for a period of time, and then they'll open it up to the public. So we think this represents a lot what we want to achieve at the Zuckerman Institute. We hope you enjoy it and you feel engaged, and we're very thankful for the support of the Stavros Niarchos Foundation, and to all of you for being here. So my job here now is going to be just to introduce the young scientist that's going to be the MC of tonight. And so it's really a great pleasure to have Shreya Saxena be the one that MCs tonight. So Shreya has a very interesting background. She did her undergrad in mechanical engineering at EPFL in Lausanne, Switzerland, and then she did a PhD in electrical engineering at MIT, but in a PhD in electrical engineering, she studied the closed-loop control of fast movements, but from a control theory standpoint. So mixing her engineering background with the interest in how we control movement. And then she joined as a postdoctoral fellow, the Zuckerman Institute, where she is a fellow in our theory center, which is one of our great assets, I would say. And there she has been looking now into the brain at how global cortical activity can explain spontaneous or more directed movements, and how the activity of populations of neurons in the motor cortex can control movements at different speeds. So when you do a movement and you start slow and then accelerate, what happens in your brain, right? Very exciting. And we're very proud. She has been doing very well, and she's now applying for positions all over the country. She didn't want this to be said, but we're very proud. So one of the things we want to do is really not only attract, but develop and support the young talent to go out there. So with this said, Shreya, if you could join me in, and please join me in welcoming Shreya. Please take this way.
Thank you, Rui. Thank you for that. And thank you all for joining us today. As you heard, I'm an engineer by training, and the neural control of movements has been one of my early interests. My own research deals with coming up with models of brain activity during movement generation. Is that good? Right, so my own research, all right, deals with models of brain activity during movement generation. And then I actually study how we can use these models to inform us about interventions that we can take when the neurons do not work as well as they should. So what got me interested in this? It was extremely powerful for me to see the effect of therapies such as deep brain stimulation for Parkinson's disease. So before the therapy, the movements are typically very shaky. So if a person is trying to reach for a cup and drink from the cup, it is very difficult to do so without spilling that liquid. Spilling the liquid in the cup, and they can't pick it up. So as soon as you deliver a stimulation to the right set of neurons, the movements magically become smooth. And I say magical because we still do not know the exact mechanisms of how this therapy actually affects the neurons in the brain and why it works. And understanding how neurons respond to stimulations such as this one will actually, in fact, help us make these therapies even better. Understanding the different strategies that we use to control our movements is also extremely interesting from a scientific perspective, and our speaker today is a pioneer in this field. Dr. Daniel Wolpert studied medicine in Cambridge, England, and before completing his PhD in Oxford. He joined the Zuckerman Institute in 2018 after having worked both in the US and the UK, most recently at the University of Cambridge. He's fascinated by how the brain controls our movements. And some of these movements are incredibly complex. And Dr. Wolpert's research focuses on why it's so hard to control these movements in a changing and unpredictable environment. He has received many awards for his work, including becoming a Fellow of the Royal Society in 2012, a great honor. On a personal note, Daniel's TED Talk really solidified my own interest in motor control at a time in my life when I was deciding which research direction to take. And so for that, I'm eternally grateful. After the lecture, I will interview our motor control expert about his research and its relevance to our everyday lives. I will then open it up for questions from you, the audience. And we particularly want to hear from the teachers and students in the audience today, so please prepare your questions already. Today's lecture is titled, What's the Brain For? A Moving Story. And I'm very excited to have Dr. Wolpert join us on stage today.
Thank you, Shreya. It's a real pleasure to be here and have an opportunity to share some of our work with you tonight. So, as you know, this is the Brain Insight Lecture, and I work in a Brain Sciences Institute. So I think we should start with the simplest question we can really ask for those who are interested in the brain. And that is, why do we and other animals have brains at all? It's a pretty fundamental question if we want to understand how brains work, to think about why we evolved a brain. Because there are many species on our planet which don't have brains. Trees, grass, they do very well, but they don't have brains. So if you think about this question for any length of time, you might think we have brains to think about the world, to perceive, but that's completely wrong. We have brains for one reason and one reason only, and that's to produce adaptable and complex movement. Now that may seem surprising, but movement is the only way you have of affecting the world around you. Now it's not quite true, there's one other way, sweating. But if you take sweating out of the picture, everything else goes through the contractions of muscles. So think about communication, speech, gesture, sign language. All that requires you to contract your muscles to communicate with the outside world. So I'm a movement chauvinist. From my point of view, sensory, memory, and cognitive processes are all important, but they're actually only important to drive or suppress future movements. There's absolutely no point laying down memories of childhood or perceiving the color of a rose if it's not going to affect the way you move later in life, because that's the only thing which can affect your survival. Okay? So remember, these are important processes, but to understand movement, we're going to have to understand sensory memory and cognitive processes, but we shouldn't forget what they're there for. So if movement is so important, how well are we doing understanding how the brain controls movement? And the answer is it's a very difficult problem. And I can illustrate that by thinking about how well we're doing building machines which can do what humans can do. So think about the game of chess. How are we doing deciding what piece to move where? If we pit Garry Kasparov here against IBM's Deep Blue, well, the answer is IBM's Deep Blue wins, and probably now would win every time. The game of Go has been solved effectively. So really, for these sort of strategic games, computers and artificial intelligence is way above human performance. But what about pitting the dexterity of a 5-year-old child's ability to move chess pieces with the best robots of today? The answer is there's no competition. The 5-year-old child wins easily. And you can ask, why is this problem so easy and this one so hard? And I think the answer is that we can all know the algorithm to solve this one. It's a very simple algorithm. Look at all possible moves at the end of the game and choose the move now which will guarantee you win. Now, yes, there's a combinatorial explosion of possible things, but with very fast computers and some approximations, we get very, very close to the correct answer. The trouble about dexterity, it's not even clear what algorithm you have to solve to achieve dexterity. And so what we try to do in my lab is try to reverse engineer and understand how people control movement. But let me give some illustrations of just what the cutting edge is and robotic end. So this is the end of a PhD at an institute in Germany, and the student has trained this robot to unscrew a top and pour out the water. Now this is not the best student, it's not the worst student, it's just an average student, what they can achieve in 3 years. And you can see it does it. It's a hard problem, but it doesn't do it with anywhere near the fluidity with which you would pour out of this bottle. Now, if you want this robot to do a different task, that's another PhD. Effectively, there's no generalization really in robotics from one task to the other. Each has to be hand-tailored to achieve a particular task. Now, I want you to compare that to Emily Fox. Here's Emily Fox attempting the world record in cup stacking. Now, maybe many of you know about cup stacking, but there might be a few who don't. Cup stacking is a popular college and school sport. You have 12 cups. You have to stack and unstack in a prescribed order against the clock. And this is her record-breaking bid in real time. Hopefully coming up. And she got the world record for that. We have no idea what's going inside her brain when she does that. And our job is to try and reverse engineer to understand how she can control her movements like that. So today I want to cover 3 sort of themes, and I'm only going to do them really rather briefly. I'm going to talk about noise first of all, and how noise affects the way we process things. I'll talk about prediction, how we predict the future, something about how we plan our movements, and a little bit about learning. So one problem which makes control of movement difficult is that it sounds an easy problem in that you generate a motor command, you send commands down your spinal cord, it causes muscles to contract, the arm changes configuration, and then you get sensory feedback from the skin, from muscles, and from vision. So it doesn't sound hard, just send down the commands to do what you want. The trouble is these signals are not the beautiful signals you want. They're extremely noisy. Now, when I use the word noisy, I use it in a technical sense in neuroscience or engineering. It doesn't mean sound. Noise means an unwanted sort of signal, unwanted process corrupting the signal you really want. So it comes from the old days of before digital radios when you were trying to tune in your wireless and you heard that was the noise on top of the signal you wanted to hear. So the idea of sensory feedback is extremely noisy. If you put your hand under a table and try to localize it with your other hand, you can be off by many centimeters due to inaccuracies and noise. Similarly, the movement command itself is very noisy. Try to hit the same point on a dartboard over and over again, you get a huge spread. And more than that, tasks we perform are both ambiguous and variable. This teapot can be full, it can be empty, it can change with time. So we work in this sort of sensory movement and task soup of noise. Now, it turns out this noise is so damaging to our ability to control movement that society is willing to reward us if we can really reduce the bad consequences. So if you're able to knock a small white ball into a hole hundreds of yards away with a long metal stick, our society is willing to give you hundreds of millions of dollars. But I want to convince you that our own brains, those of us who are not expert athletes, go to a lot of effort to reduce the negative consequences of this noise. And to do that, I'm going to tell you about a framework called Bayesian decision theory, which is a framework which tells you how to be optimal in the face of this sort of noise and uncertainty. And it comes from this man, Thomas Bayes. He was a British cleric in the 1700s, wasn't particularly famous during his life, but after he died, a friend of his found an interesting mathematical proof among his papers and thought it so interesting, he decided to send it into the editor of the Philosophical Transactions of the Royal Society, saying, I now send you an essay which I have found among the papers of our deceased friend, Mr. Bayes, and in which my opinion has great merit. Now, we're very lucky that the editor then was not as difficult as he is today and didn't ask for major revisions. And instead it was published as essays towards solving a problem in the doctrine of chance. And it was really forgotten about for hundreds of years. But from the 1950s or so onwards, it's become a major part of statistics and machine learning. And more recently, a sort of unifying way to think about how the brain may deal with uncertainty. And the idea is that what we would like to know, what I'd like to know, is how does sensory input we perceive get turned into motor outputs? That would be really what I'd like to know. That would be understanding motor control. The trouble is that single transformation is very hard. But Bayes' rule gives us a way to break that down into a set of steps at least, which makes it a little easier to think about. And key is that you want to generate beliefs along the way. And a belief can be anything. A belief can be, are my arms in this configuration or this configuration? Am I looking at a cat or a dog? So you want to generate beliefs. And Bayes' rule tells you there are only two sources of information you can use to generate belief. You can use data. And in terms of the brain, data comes as sensory inputs. That's all we get. We can sense the world. There's nothing else data coming to us apart from through our senses. But also, we could have stored knowledge. We could have prior knowledge stored in memory or genetically encoded. And what Bayes' rule tells us is we should use both our sensory inputs and our prior knowledge to generate our beliefs. And given our beliefs, we might want to generate actions in some optimal way. Okay? That's the idea. And key to Bayes' rule is an idea that we represent things as probabilities. We don't just say a belief is true or false. We're allowed to say the probability it's true or false. I'm reasonably sure, I'm not so sure, numbers between 0 and 1. Now I'm going to be very mean and show you an equation because it's so beautiful. Doesn't matter if you don't follow the equation. It won't affect your enjoyment of this talk, I hope. But what we really want to estimate in Bayes' rule is the following. We want to estimate this is called the probability of different states of the world. This vertical line means given sensory input. So how probable is it my arms are in this configuration or this configuration given the sensory input I'm now getting? How probable is it I'm looking at a cat or a polar bear given the visual information I've got coming in? That's what we'd want to estimate. That's what we really want to know, and that quantifies our belief. It's sort of a number between 0 and 1. 0 means I'm sure it's not that state. 1 is I'm totally sure, and numbers in between give me my grayscale. But what Bayes' rule does, it lets us do this in 2 steps. It tells us the 2 components we need to calculate this. This component over here is my probability of different states of the world existing independent of what I'm sensing. That is, how probable is it my arms will be in this configuration or this configuration? Or how probable is it I'll today see a polar bear compared to a cat? So these are things I can store by my experience of the world. If I just ran on that, it would be like hallucinating, because I'd just be going on the most probable thing to happen. So I have to ground that with reality, and the way I do that is I calculate this thing here, which tells me how probable is my current sensory input given possible states of the world. And if I multiply these 2 things together, I get what I want. It's my belief after sensory feedback. So it's a way of combining prior knowledge with sensory information to estimate beliefs. Let me give you a real-world example. You're playing tennis, a nice motor task, and you want to estimate where the ball's going to bounce as it flies over the net towards you. Bayes' rule tells you there are 2 sources of information. You can use sensory input. You can use vision. You can use audition. And maybe based on that, you estimate this thing here, which is this red cloud there. So it's most likely there, but you should know that your senses are not perfect. And therefore, there's a small chance it could land here and a very little chance there. The information to calculate this red distribution over the court is available in the current shot, but there's other information you could have stored that you may know the way your opponent tends to play or the distribution where they might send it over the court. The ball doesn't bounce with equal probability over the court. Maybe your opponent's going to aim for the sort of green area here. And if you knew that, your optimal thing to do would be combine these green areas and the red by multiplying the numbers together over the court to get the optimal location shown here. Okay. And to do that, you'd have to learn statistics of the outside world, and you'd have to know something about how noisy or unreliable your own sensory apparatus is. Now, I'm not going to take you through the data, but there's plenty of data from our labs and other labs now showing that over a range of motor tasks, people are very good at representing the distribution of tasks, statistics, knowing about their sensory uncertainty and combining them in a Bayesian way. So we really are Bayesian when it comes to these sensory motor tasks. Now, it's hard for me to prove that to you here, because for these sorts of tasks we do in the lab, you have to come into the lab, collect a lot of data, and analyze it. So I'm going to give you some other examples which comes from vision and audition, which also have Bayesian explanations, to give you some intuition of how Bayes might explain things which seem sort of mysterious. So if you look at this object here, and you look at the diagonal, you'll feel like those dots in the diagonal are coming out towards you, I hope. Now, all I'm going to do is just turn that image upside down, doing nothing else, and just focus on the diagonal, and hopefully you'll all get the impression that now they're all going in. Okay, nothing else has changed. I just turned it upside down. And the reason this is a totally ambiguous stimulus. It's just a flat thing on the screen. All it is circles which are sort of grayish on one area and lighter on the other area. There's no way to tell whether these things are coming in or out unless you have prior knowledge about where lights come from. And we live in a world where the sun and moon tend to be above us, lights in the room tend to be above us. So you have a strong prior that light shine from above. So in this image, if something is light above and dark below, it must be sticking out. And if it's dark above and light below, it must be going in. So using strong priors. If I put you in a room for 3 or 4 hours where light shines from below and you feel objects, this prior begins to change. So the priors are adaptable. Another example is the Necker cube. Here's a Necker cube. You'll all see this as a cube. It's not a cube, it's just a bunch of lines on a bit of paper, but you see it as a cube. Why do you see that as a cube? Because in fact, all these objects, and there are infinitely many of them, give the same projection of this image on the back of your eye. So there's an infinity of objects that could be, yet you see it as a cube. And the reason is we can go back to Bayes' rule. And Bayes' rule says that given all these possible objects, the probability of the sensory input is the same. It's definitely going to be this image here. So this doesn't tell you anything. But how probable are these different objects in the real world? Well, cubes are extremely common. So effectively, you see it as a cube because that's the commonest interpretation for that image on the back of your eye. And it also applies in auditions. So I want you to watch this man. He's going to speak to you, and your job is to decide, is he saying da da or ba ba? So have a listen.
Ba ba, ba ba, ba ba, ba ba.
Now I'm going to expect that most of you heard da da there. Okay, great. Listen to him again.
Ba ba.
And whenever you feel like it, close your eyes.
Ba ba. Ba ba, ba ba.
And open them and look at them again and see whether your percept changes.
Ba ba, ba ba. Ba ba.
Okay?
Ba ba, ba ba.
So you can convince yourself that with your eyes open, you hear da da. With your eyes closed, you hear ba ba. That's crazy. But it's not crazy because effectively there's noise. When you hear things, it's hard to perceive because there's variability. So in fact, the way that movie is created is the sound you're hearing is ba ba, but you're hearing a noisy version of it. And the video is someone saying ga ga. But you use both the visual and the auditory information to try and decide what the person's saying. And what Bayes' rule tells you is you'll do an approximation between them, which is da. If you close your eyes and remove the vision, then you're going to hear the ba. So it's really a very precise way of explaining these odd phenomena that you're trying to resolve uncertainty. Okay, I want to move on to talk a little bit about prediction. Because this part of Bayes' rule says I need to say how probable is the sensory input I'm getting now given different states. And that's really a prediction. I have to say, what do I predict I'm going to get, and then compare it to what I really get. And so to do that, we have to think a little bit about the transformation. You send movement commands out, and you get sensations back. And that transformation is governed by the physics of the body and the sensory apparatus. But we and others hundreds of years before us have suggested that within the brain, you might have a neural simulator of this physics. So the idea is you would tap off a copy of that command. Here's a copy of the command you're sending down. And within the brain, you'd have a little neural simulator which would predict the sensations you're going to get. So as I go about my daily life, I'm moving. Not only am I getting the sensory feedback, but I'm predicting what I'm expecting to get. Why would I bother to predict something I'm going to get anyway? It doesn't seem very useful. But it turns out such prediction is really useful for a whole host of reasons. And I'm just going to give you two today. One is that it takes a long time for the motor command to go out, contract the muscles, and sensations to come back in. And when you drive a car which is not very responsive, it's very hard. And so waiting for that feedback is a pain. On the other hand, if you can predict ahead what you're going to get, you don't have to wait for that feedback. You can actually use your prediction to drive movement. So for those of you, and this has become more common in the States and in England, many of you will have water bottles with you now, and you can try this out if you've got one. If you put a water bottle in your hand, a nice heavy water bottle or a book, and then effectively you use your other hand to lift up that water bottle, what you'll find is the supporting hand won't move at all, not at all. If you get a friend to lift the water bottle or the book off your hand, you won't be able to keep that hand still. It'll either go up or down depending on what force you're generating. And so the way we think you can do this task, you do it yourself, is you anticipate what's going to happen in the future and can use this arm then to unload or reduce the force you're pushing up with in a very precise way. So effectively by predicting, it really helps with our dexterity in terms of when we interact with objects. But there's another use of this prediction, and that is to filter off information which is not so useful. So here's the information I'm getting, the sensory feedback as a function of time due to me shaking this ketchup bottle. But very kindly, someone's coming up and tapping on it at the same time. So they're tapping on the bottle for me, and I'm going to get an input due to that external event. So you're tapping on it, I'm shaking it, but all my receptors get is a combination of those two things. And in general, we want to be more attuned to external events. It's much more important to know what's going on in the outside world than to feel all the things I'm doing to myself as I move around. So one way to recover what you're doing is to subtract off the prediction based on my command. So I subtract that off from the total, and hopefully I recover you. So the idea is as I go around the world, I subtract off everything I can, everything left over is an external event, and that's more important. So we thought, what way could we test this idea in humans that you're subtracting off predictable sensory events? And there's one very clear example where doing something to yourself feels very different from when it's done to you. And so we decided to study tickling as an example of maybe the reason you can't tickle yourself is maybe you're making these precise predictions. Okay? So we're going to bring tickling studies into the 21st century by applying robotic technology. Okay? So here's a robot attached to a little stick, and this robot can move around, you can move the stick around, and we can track that robot and use a computer to control another robot which has got a stick which is going to tickle the subject's palm. And we ask subjects to move back and forward here, and then we tickle them here, and we ask them to rate the tickle sensation. Okay. So the first thing we do is just replicate old studies with our new apparatus. So I'm not showing you the robots here. Subjects move back and forward, and we replay that as accurately as we can in real time so that the stick follows them. So if we get this right, it's like just doing it with a solid object, even though the sticks are separate. And we can, in the same subjects then, have this hand stationary and just replay the same tickle to the other hand. So they're getting the same input to the left hand, but what we find in this situation is significantly more ticklish. Okay, that's not surprising. So when you tickle yourself, it's less ticklish. But there are various options here. One option is maybe the brain, when it does something, just turns down the whole volume. It just says, oh, I don't care about what I'm getting. I'll just turn down the gain or volume of the feedback. Or it could be it makes a precise prediction both in space and in time. So to distinguish between those two, we can put some perturbations in. Now the subject moves back and forward, and we replay that to the other hand, but now with a time delay. A small time delay, 0.1, 0.2, or 0.3 seconds. And as we introduce a time delay of 0.1 a second, it becomes more ticklish. 0.2 seconds more ticklish again, and by 0.3 seconds of a time delay, it's equivalent to the robot just tickling them. So this suggests that whatever is responsible for cancelling the tickle sensation is extremely sensitive to the temporal causality. As you mismatch what you expect to get here by adding in a time delay, it pops through and you get the tickle sensation. Instead of putting a time delay in, we can put a rotation, and the hand goes in one direction and the tickle goes at 30, 60, or 90 degrees. And again, as there's a mismatch, it becomes more and more ticklish to the point where it's equally tickling to the robot. Importantly, we have to interleave all these conditions to make sure people don't learn these new rearrangements. But I think this really shows that when the reason we can't tickle ourselves is you make a precise spatial and temporal prediction. We've done lots of other studies since then these in which we look at force cancellation and other things where we can show really people when you make actions, you discount the force you produce. So that when you hit someone else, because you're active in that generative motor command, you think you've hit them lighter than you really have. So if they hit you back with the same force, you think they've escalated. So prediction's an important part of control. But there's no point really generating all these beliefs from this Bayesian without actually then generating the action. So we need to think a little bit about how do we generate actions. And one interesting thing about the motor system is that any task we have to produce, we have more infinite numbers of ways we could achieve it. So for example, if I want to move from this point in space to this, I could choose to move along this path, or infinitely many other paths. If I choose a particular path, I can hold my arm on that path with infinitely many different joint configurations. And if I choose a particular joint configuration, because I've got muscles which could go across joints, I can hold my arm there really stiff or really relaxed. So I've got a lot of choice to make when I generate movements. So it could be that we all choose our own sweet way to do our movements, or there could be some principle about the way we move. And it turns out in hundreds of rather tedious studies, it's been shown that people are very stereotypical. We all move roughly the same way when we walk, when we reach, when we eat. There's some variation, but we're very similar. And in fact, we're so similar that there are dedicated neural circuitry in our brain to interpret biological motion. So if things move in the way that humans move, it's very easy for us to work out what's going on. So for example, if I take these dots here and I set them in motion, you'll instantly know what's going on. You'll know whether this person's happy or sad, male or female, old or young. Even though this is just a bunch of dots moving on the screen, because it's biological motion, it's very easy to interpret. If this was cars going around a racing circuit, you would have no idea. Similarly, if I set these dots in motion within a tiny fraction of time, you know exactly what's going on. So we're very stereotypical. Of course, we don't have to be, and people can make their early careers simply by violating biological motion. Okay? For somehow, you know, when people violate the normal biological motion, it seems like funny and unusual to us. So we don't have to move the way we do, but for some reason we choose to. And so the question is, why do we move the way we do out of all the possible ways we can move? And maybe we don't all move the same way. Maybe there's variation in the population. And those of you who move better than others have got more chance of getting your children's next generation. So maybe on evolutionary timescales, movements improve by some measure. And maybe through life, you try to improve your movements, you know, through learning. And the question then comes, what is it you're trying to improve? What is it about the movement which specifies the way you move? And we can come back again to the idea of noise. We're very variable with our movements. You try to make precise movements over and over again, we get a lot of variability. And if you look at the details of the variability, they're quite interesting. So if you ask people to generate a force just against a little transducer, so you can measure the force of, let's say, 1 Newton, 2 Newtons, 5 Newtons, and you measure the force they produce as a function of time, you get fluctuations. And the fluctuations you get bigger with the bigger the force. So the more force you produce, the more variable you are. And we call this signal-dependent noise, because the amount of noise, this variability, scales with the signal. Okay? And that's really rather unusual. Mostly in engineering, you have this sort of constant noise added to the signal. This is a signal, this is a noise which scales. But it might allow us to answer why we move the way we do. So imagine I gave you a choice. You're going to catch this ball by moving your hand to this point, which is the same as this point. And you could choose to move along this path or along this path out of the infinity of paths you could choose. And let's think about whether one of those might be better than the other. Well, if I move along this path here, it specifies the sequence of commands I need to contract my muscles. So here, schematically, maybe is the motor command sending to one of the muscles, let's say biceps. That's what I want to happen. That's my desired command. But because of noise, I get a noisy version of that, with more noise for big commands and less noise for small commands. Now, if I was to restart the hand at the same point, same desired command, the noise will be different, so I'll get a different movement. So if I was to replay the movement many thousands of times, I could say what would happen to the variability of that movement over the course of the trajectory. And maybe it'll look like this. So this shows the variability of where I'm likely to end up if I choose to move along this path. If I move along this path, I'll need a different motor command, noise will be added at different times. It's impossible to intuit what the variability will be, but you can simulate it, and maybe the variability in this case will look like this. So the idea is a sequence of commands leads to a distribution of possible outcomes of the movement in terms of the position, the velocity, the force, the joint angles, and so on. And so if we can specify what we care about in terms of the probability distribution, what we care about for the particular task, what do we desire to constrain? So we could decide, for example, we could squash this ellipse in one way, but it'll pop out other ways. Then we can say, then we can ask what the optimal sequence of motor commands. Then we can ask what's the optimal sequence of commands to achieve that desired behavior. So this really gives us biological plausible underpinning for like goal-directed movements. Noise affects the ability to achieve the tasks, and so you want to choose a way to move to minimize the bad consequences of this noise. And I'm not going to take you through all the papers, but if you apply this to eye movements, arm movements, you can predict the stereotypical patterns of the movements we tend to make based on this simple principle. Okay? Effectively, there are two things we care about. One is accuracy, the other is energy. If you want to model things like walking, energy is more important. When it comes to feeding yourself with a knife and fork, it's much more important to get the fork into your mouth than into your eye, and you don't mind wasting a bit of energy for that. Okay. In the last few minutes, I want to talk a little bit about motor learning and just give you a feel of how we study that in the lab. And the way we do that is we think about the problem of learning things which are new. Now, if you bring someone into the lab and you give them some tool, you can't be sure they haven't seen the tool before or the task before. So we go to a lot of effort to generate really novel experiences where we can be pretty much sure you've never experienced them before. And to do that, we build robotic interfaces which can perturb your movement in computer-controlled ways. So we have two-dimensional robots and three-dimensional robots. And so if anyone wants to come and experience our robots, well, we're always looking for subjects. If you're right-handed and 18 to 45, you can go to this website and you can come and earn money, do our experiments. I can't promise experiment you do will involve a robot. We do other experiments which don't, but some of the robot ones are quite fun. So what we do with the robots is we'll sit someone down and ask them to move their hand from one point to another, to a target. And as they do that, the robot will generate a force on their hand in a very precise way. It'll produce these forces, and the force we might use in this experiment is one where the strength of the force is proportional to the speed of the movement. So the faster you move, the bigger the force, and the force always acts at right angles to your current direction of motion. So we call this a clockwise field. It acts in a clockwise direction. Whichever way you go, pushes you round in a clockwise direction. And if you experience that force field, what will happen is you'll get perturbed off. And over the course of 20 minutes or so, if you just keep doing the task, you'll straighten up your movement till you're doing this lovely straight movement. And more than that, you will no longer perceive the robot to be on. You'll think it's been turned off. Because again, you predict what's happening now, and you no longer feel those forces, because it's now part of your sort of internal model of the world. Right, so we can do a clockwise force. We can also do a counterclockwise force, opposite. Okay? And what we can do is we can basically alternate. So I'm showing them different points in space. It's really the same point in space. Every trial, we can randomly choose whether you're going to do this field or this field. Now, if we do that, it's really unfair, because you don't know what field you're going to do. There's no way you can learn it. So we can be kind to you and tell you, if the light is on here, you're going to get a force field pushing you one way. And if this light is on here, you're going to get a force field pushing you that way. And we just randomly alternate, this field direction with a light. And you'd think that would be something easy to learn, but it turns out it's really hard to learn. And the way we measure the learning is occasionally we put the light on one side, and we use the robot to constrain the hand to a channel. So from the subject's point of view, they go, wow, I did a great job, completely straight. But what we can do is we can measure the force they produce into the channel wall as a marker of what they've adapted. So in this case, if they've adapted to this force field, they should push to the left to compensate for this rightward force. And then we can actually plot adaptation. So if we do this experiment, here's adaptation, no adaptation, full adaptation. And if we alternate these randomly, subjects effectively learn nothing at all. So you can't use this static visual cognitive cue to learn these two memories at the same time. But we can change the experiment just a little bit to get very nice learning. Rather than start from here, we'll tell them to start from the light, make a movement in to this point, and then go through the force field. And the direction of this lead-in movement, either from the left or the right, will predict the direction of the force field they're going to get. So if they come in from the left, they'll get a right force field, or from the right, they'll get a left force field. And in different groups of subjects, we're going to make them wait at this point for different amounts of time. So if subjects have to wait a second here, there's no learning. But if we only make them wait half a second before they go through this, we begin to see learning. And if they only have to wait no time at all, we see really substantial learning. So it seems that what you do in the sort of recent past, in the last 500, half a second or so, allows you to separate out these two memories. Okay? And believe me, learning these opposing force switch trial is really not easy, so this is a powerful effect. So it suggests the past may be an important predictor of how we separate memories. So then we thought, let's do something crazy. If the past is important, could the future also be important? So we have one group of subjects, our control group, who again make a movement through a force field, and either this target is on or this target, but they can ignore that, although it tells them the direction of the force field, and we see no learning in this group. But we have another group where we say we want you to follow through after the movement. So go through the force field and either follow through to the left or follow through to the right. So what they're going to do after the skill is predictive of the field they're going to get. And the group who gets to follow through, we see substantial learning. So it suggests that what you're going to do in the future can allow you to learn separate memories for these two opposing force fields. And the reason that's interesting to us, for one reason it's interesting to us, is in sports, people are always told to follow through. Yet we know that once you let go of a ball and make contact with a ball, it can't have any effect on the flight of that ball. So why should it be important to follow through? Well, if what I've told you is true, then if when you learn a skill, you always do the same follow through, you will be putting all that learning in one motor memory. Okay? If on the other hand, when you learn a skill like this and you do a different follow through each time you do the skill, you'll be spreading that learning over multiple memories and it may be slower. So we did exactly this experiment. One group of subjects learned just a simple force field, there's no switching now, just one force field with a consistent follow through. Another group did a follow through where the follow through was different each trial. And what we found is the group with a consistent follow through learned significantly faster, shown in here in red. So it suggests that perhaps one reason you need to follow through is that it allows you to consolidate that learning into a single motor memory. So I study the control of movement because I think it's a fascinating problem for the brain. I think it is what the brain is there to do, is to generate movement. And so to understand the brain, we have to eventually understand movement. But of course, about 5% of us are affected by motor diseases in our life. So there are many diseases which affect motor control. So understanding the basic mechanisms of motor control allows us to understand what goes wrong in disease. It also allows us to think about rehabilitation programs. If we understand normal learning, can we harness that normal learning to help people who have strokes or cerebellar disease or other diseases? And of course, if we really understood the control of movement in the brain, we could apply that actually to robotic interfaces to improve them. Now, I want to finish really by talking to the students in the audience, if there are some. I think it's really important to think about the computational approach to the brain, using maths to understand the brain. I'll give you a personal reason. Back in 1982, I was a medical student, and the first edition of this book, Principles of Neuroscience, which comes out of Columbia, had just come out, and at that point it had 740 pages, okay? And I can have to tell you that's a lot of pages to have to pretend to read, I can tell you. But in the intervening years, there've been another 4 editions, there's another one coming out next year, and we can ask, how are we doing generating new principles of neuroscience? And the answer is doing very well. Look, it's going up. We're at 1,500 pages. I don't know how many pages are going to be in the next textbook coming out next year. But now I can ask the question, if my grandchildren went to university and read neuroscience, how many pages of principles will they have to read? Well, look, I can fit a linear regression, R squared 0.96, and the answer is about 3,000 pages of principles. Is this a good thing? Is it lucky them? I would argue it's not lucky them. I would argue there's a problem with this curve. And the problem is very clear. There are too many experimentalists out there doing amazing experiments. I'm not against experiments. Experiments are really important. But the trouble is, if you go to Society for Neuroscience, our big meeting of the year, there are 30,000 neuroscientists at that meeting. This is just a picture of one of the poster halls to give you a feeling for the scale of this meeting. 30,000 neuroscientists, and I would expect that 99.8% are experimentalists doing great experiments. But it's really the duty of the new generation to learn the maths, do the theory, to apply pressure to this curve with the hope that we can bring this curve down to where it deserves to be. A book of principles, not a book of all the experiments which can't be encapsulated in principles. If not for ourselves, we should do it for our grandchildren. Okay. I didn't do this work all by myself. This is just a few of my collaborators, but there are many others I haven't mentioned here. It's a really collaborative effort, and it's an exciting place to be now in New York in this new center, which is really an exciting collaborative opportunity. But I want to remind you now that when you see simple creatures doing motor-controlled tasks, don't be fooled by the simplicity. There's real complexity going on inside their brain. Thank you very much.
Thank you for the wonderful talk. That was really nice to hear. So I'm going to start with an easy question. So you mentioned at the beginning of your talk that the brain is basically to make movements, That's the one goal. So I have a simple question for you. I have so many neurons in my brain. Why can I not put a USB the right way around in the computer the first time? Why is that so hard?
Well, there may be a few reasons to that. One reason is your life may not depend on it. So we can do things which really matter to us, in terms of survival. So if you couldn't get food into your mouth, I'd be more worried. But USB getting it the right way around is not such a problem. It's not something we've evolved to do necessarily, so I wouldn't worry too much about that.
Okay. I won't worry about it. On a more serious note, people have recently found in mice studies primarily that a large part of the mouse brain is active when the animal is moving. So that was surprising in the field, but they should have just talked to you first. But what are your thoughts on, a large part of the brain, including visual and sensory areas, which are not traditionally thought to be encoding motor activity. What are your thoughts about these experiments?
I think it's great. I try to tease my colleagues, because in neuroscience, as I said, there are 30,000 people. They tend to be in silos. There are people who work on vision, people who work on audition, people who work on memory, but they don't think about motor control. I think it's going to be very hard to understand, for example, vision without realizing it actually has to drive action in the end. There's no point processing visual things which aren't going to affect the way we move. So I think the idea those signals are there is absolutely great. And also, I think we also have to realize that movement isn't just there to achieve tasks. Because all our sensory apparatus is on our body, like my eyes are in my body, my hands are attached, the way I move affects the sensory information I get. So we actually think about what we call active sensing, the way that you want to choose to move to get good sensory information. So we've done experiments recently asking, is the way I scan the world with my eyes to try and get the information I want from the world? So I think those signals, or most signals being there in the sensory areas, could easily be a part of the active sensing strategy, that you want to get good information, and you need to know what you're doing with the motor system to get those.
Yes, cool. So you touched upon this near the middle of your talk. A lot of the goals of this research, while trying to figure out scientific principles, is also how we can actually use them for rehabilitation and diseases. So I guess I was wondering if you could speak a little bit more towards that, and how directly may be used.
I would be honest to say most of our work is blue sky. So we're trying to work out the algorithms. We think that understanding the algorithms would then allow us to go into the physiology and interpret physiology better. But the hope is that we can use some of these understandings to help with diseases. So people are beginning to use these sort of robotic devices to try and rehabilitate people who have stroke. I'm involved in a project actually with Johns Hopkins University looking at cerebellar patients. So cerebellar patients find it very hard to reach because they can't use the error information effectively to correct their movements. But there are other ways you can train people which don't require errors. For example, you can give people real success or failure, a bit like a child looking for a room when you say hotter, colder. So if you use that sort of training with cerebellar people, they can actually then learn to reach better than by giving them error feedback, because it gets into different circuits, for example, which do reward. So we're beginning to understand those sorts of things and try to harness that sort of knowledge. But it's a hard problem, and we're still far off, I would say.
Yeah. And on the other hand, how do you think this work can be used to make our movements even more optimal? So,
yeah.
You mentioned the baseball. Are there other kinds of the follow through? Are there other kinds of these tricks that one can use to how can I
think at the moment, a lot of sports will come after I do the tennis and say, how can I play better tennis?
Yes.
If you think about the noise I talked about, I don't believe we all have the same noise. I don't believe Tiger Woods and I have the same signal-dependent noise. So although I think we all have this noise which scales, the way it scales can vary from person to person, as we've seen in the lab. So I expect some people are just born somehow with less noise and therefore can make those movements. The other alternative is that it's just practice. We all got the same noise, and if I just practice more, I will get there. I don't believe that. And the third option is actually that says that the way noise plays through the body depends on the physical structure of the body. So in England we have darts, a very popular sport, and most darts players are very large men. And it could be that the way noise plays through a very large body actually dampens down the noise, making them a very good darts player. So it could be that changing the physics of our body might help us with these sorts of things.
So you're saying I should gain weight?
No, only if you want to play darts.
Better.
I think it's only good for darts.
Got it.
but yeah, so we don't, we tend to work with undergraduates. We're not looking at skilled players, but I think it would be interesting to see whether some of these follow-through ideas could help the sports.
Yeah,
But I think the sports people are very good at stumbling across the right ideas without knowing why.
Yeah, and you mentioned that you do all these sort of experiments in your lab where you have these robots and force fields and things like that. Have you had subjects that come in, so you take anyone off the streets, right, basically. Has anyone done something completely unexpected where they just used it the wrong way? Or
Well, not unexpected. So the worst subjects are other scientists, because rather than just do the task, they want to try and figure out what the experiment is about. And so they play, rather than just reach, they just try to experiment. So basically physicists are the worst, because they really want to know. Neuroscientists aren't too bad, they're happy to do anything. So we tend to, we can't put on our ethics form no physicists, apparently it's not allowed.
only neuroscience or random people. Cool. And I guess on a more personal note, how did you get started in this research? Is there,
Yeah, it was a little random. So, again, it's interesting. With 30,000 neuroscientists at our meeting, there's a huge range of topics one can go into. And I don't know, it's very hard to consider them all and say you make an objective decision. So what I did after I finished medical school, I wanted to do a PhD, and I was going to do one in epidemiology. I was interested in modeling population dynamics. But I bumped into the professor who was looking after my medical training. He said, "Oh, you don't want to do that. Epidemiology, that's not where it is. It's the brain. The brain is what you want to model. That's the interesting thing." And he showed me a paper in Nature, and he said, "Read this." And I said, "This looks great. So interesting. Yes, you could come and work with me. We could do this sort of stuff." And he conned me, so I went to work with him. He didn't understand the paper at all. he just knew it was interesting. So, and he happened to work on motor control, so I got into motor control. But there's a nice thing about motor control. It's a less developed field, I would say, than the perceptual field. So, historically, people have worked on vision as the thing to work on. And I tease the vision scientists, look, I'm absolutely fine without vision. We had many MPs without vision. You can do absolutely fine, but you lose control of movement, you're really in trouble. So movement is really a fundamental part of life, perhaps more than vision or audition. So I'm glad I'm in that area.
Who was the paper by?
It was by Zipser and Anderson. It was a neural network model of parietal cortex.
I'll have to read that one. And I guess, again, so you recently moved from the UK to the US, to New York. How are you liking New York? Has a typical day in your life changed significantly
yes,
after having moved?
it's very different. So I was in the engineering department there, and I think it's a delight to be in a very strong neuroscience department. And one of the beauties of where we are in New York is the institute covers everything from molecular up to behavior and cognition, and so that's great. And it has an incredibly strong team working on motor control, and so that's it's unique anywhere in the world, I would say.
Thanks, Jerry, you're here. Great. And is there, so I know you have kids, so is there something that you were kind of doing differently while teaching them how to move that you think was helpful because of this
research? They move on their own. But I mean, there were a few things I learned from them. So it was really, on back seats of cars on long journeys, children do the following. I'm sure you're used to that. One touches the other touches them back, and they get into this tit-for-tat fights where you scream at them. And my children would do that, and they both would claim that the other person hit them harder. And this is when we were doing the Tickling studies. And I know my children never lie. So I thought, how could it be they both think they've been hit harder? And so we hypothesized based on the Tickling study that maybe when you hit someone, because you're active, you predict the sensation and cancel it off. But you as the passive recipient feel the full force. So if you apply the same force back, it feels like it's escalated. So we decided to do experiments in the lab based on that. And we did a tit-for-tat experiment where you touch someone and they touch you back and you measure the force. And you're told to do the same force, and what you see is the force rapidly escalates. And then we did a bunch of control experiments to show it really is prediction, that effectively these forces escalate because you underestimate your own things. So I could forgive my children, we had an explanation. And that actually led to a very, very fruitful line of experiments which even explains some of the symptoms of schizophrenia. So schizophrenics hear voices which often they articulate themselves. And the idea is I can hear a voice in this room at the moment, but I know it's me speaking because I'm predicting what I'm going to hear, and it matches. If you speak, I don't predict that it's you. But if you fail to predict that voice, you can be surprised by your own voice and think it's coming external to you. And so we did some studies of this cancellation in patients and showed they don't cancel. So they can't tickle themselves, for example. So they can tickle themselves, is what I'm saying.
That the forced escalation also may explain a lot of current political problems
It,
in the world.
it may well do. Yeah.
Okay, final question. What comes next? What are you currently working on in theory or
Well,
experiments?
okay, so I'm working on many things. So we're carrying on with our current work, which is a lot of models of motor learning. So we've got new models of motor learning, trying to link to decision making, trying to understand active sensing. But part of what I want to do in coming here is to get involved with collaborations with the animal type work, which I think is really important. Because I think if you really want to understand it, we have to link these algorithms to their neuroinstantiation. And that's what's really exciting me. And that's already started to happen since I've come here.
Sounds amazing.
Okay.
Well, now I'd like to open it up to questions from the audience, from you guys. So my colleagues will pass around the microphones here, and please put your hand up as someone already has.